Professor Loeb says that based on his calculations, it looks like 3I Atlas has been losing an extreme amount of mass, which could mean it's exploded into a dozen smaller pieces.
Fresh calculations from Harvard's Avi Loeb suggest 3I Atlas underwent catastrophic disintegration during solar passage, fragmenting into potentially millions of distinct pieces.
We see a fragmented object where the pieces will get separated from each other by the tide from the sun.
The physics is quantifiable, the mathematics precise, the implications extraordinary. Yet that natural explanation, as dramatic as it sounds, might be the simpler scenario, because there's another possibility, one Loeb himself has laid out with equal scientific rigor, and the observational window to determine which narrative reflects reality is collapsing fast. Here's the physics problem nobody anticipated. Energy calculations demand a nucleus measuring at least 14.3 kilometers across to produce the mass loss rates 3I Atlas displayed.
Carbon dioxide requires a surface area of an object that is 20 kilometers in diameter, much bigger than we estimated for the actual nucleus of 3I Atlas.
But Hubble imaging from July 2025, captured 3 weeks post-discovery, constrained the diameter to roughly 1 to 2 kilometers maximum. That's a 16-fold discrepancy. You can't hide 14 kilometers of ice and rock from the Hubble Space Telescope's optics. Stop. This next detail contradicts basic cometary behavior observed across every cataloged solar system comet. The object was turning bluer. Comets, heated by solar radiation, typically glow yellowish-white as dust particles scatter sunlight across longer wavelengths. 3I Atlas shifted toward blue wavelengths during approach, suggesting metallic compounds reflecting light in ways standard icy nuclei don't.
This morning we have a report that the object got much brighter than expected, and moreover, the color of the object is blue, bluer than the sun, and that's very surprising because usually when there is dust around an object, it should make it red.
Picture a snowball that becomes shinier and more metallic the closer it gets to a fire. That doesn't occur in known natural processes. Standard physics offered outgassing as the mechanism. Volatile ices sublimating under solar heat, material jets creating reaction thrust. From early August through perihelion on October 29, sublimation rates escalated from 330 kilograms per second to approximately 2 million kilograms per second. That's a 6,000-fold increase. Daily mass loss shifted from sub-million ton rates to ejecting 2 million tons per second at peak. But here's where energy balance shatters the conventional model. Solar radiation delivered 700 joules per square meter per second to 3I Atlas at perihelion. Loeb's calculations determined that sublimating sufficient carbon dioxide and water ice to match observed mass loss required at least 617 square miles of absorbing surface area, equivalent to a sphere 14.3 kilometers in diameter.
In order to get that much mass out of ice, we need a large surface area of an object. And it turns out that it's a surface area of an object that is at least 20 kilometers in diameter, much bigger than the original estimate for the size of the object. So that would mean for a natural comet that it was broken up into many pieces such that the surface area, the total amount of surface of these many pieces adds up to the amount of mass that we need to release.
Yet Hubble's July observations capped the nucleus at 1 to 2 kilometers. Only one mechanism reconciles the thermodynamics: catastrophic disintegration into millions of smaller fragments, each presenting independent surface area. The collective thermal exposure would match energy demands. The mathematics forces this conclusion. On November 9, 2025, 11 days after perihelion passage, British Astronomical Association observers Michael Butner and Frank Nebling documented imagery that transformed the investigation. They didn't capture a diffuse debris cloud characteristic of thermal breakup. They photographed organized, collimated jet structures. An anti-tail formation extended 950,000 kilometers toward the sun, defying standard solar wind dynamics that push material outward. The primary outflow stretched 2.85 million kilometers in the opposing direction, approaching double the Earth-Sun distance. Additional imaging resolved at least 7 distinct jets displaying geometric organization, precise directional patterns inconsistent with chaotic, explosive fragmentation. Most observers will overlook what this geometry actually implies. But if you're tracking the measurements, you're witnessing something unprecedented. Debris fields from thermal stress should create randomized particle distributions. These jets showed structural coherence, as if material was being channeled rather than passively released. Loeb calculated that maintaining 50 billion tons monthly in sustained mass loss would require either massive intact nuclei, contradicting the fragmentation hypothesis, or millions of fragments somehow retaining extraordinary outgassing capacity. Natural physics struggles with both scenarios simultaneously, which brings us to Loeb's controversial alternative framework. If standard cometary outgassing cannot parsimoniously explain the observations, the organized jets, the sustained mass loss from countless small fragments, the geometric patterns, then technological propulsion mechanisms enter the analytical framework. Advanced propulsion systems achieve far higher exhaust velocities than sublimation processes, requiring dramatically less propellant mass to produce observed accelerations. Directional thruster arrays would create exactly the kind of collimated, geometrically organized jets November photography revealed. What observational data reveals, and Loeb has explicitly stated, is that upcoming telescope campaigns will resolve the ambiguity. He's not claiming proof of artificial origin. He's framing competing hypotheses with equal scientific rigor, acknowledging that fragmentation remains viable, but demanding the measurements decide. Hubble's November spectroscopy and Webb's December imaging will either reveal debris fields confirming natural breakup or show structural anomalies forcing entirely new interpretations. Then came trajectory measurements that stopped mission planners cold. 3I Atlas was accelerating beyond what solar gravity alone could explain. The object gained roughly 94 kilometers per day squared at closest solar approach, already traveling beyond 150,000 miles per hour, and somehow accelerating further. Forces don't materialize from nowhere in celestial mechanics. This visitor entered detection range July 1, 2025, spotted by Chile's Atlas Survey telescope, humanity's third confirmed visitor from beyond the solar system, joining Oumuamua's 2017 flyby and 2I Borisov's 2019 passage. 3 detections in 8 years suggests interstellar visitors may be far more common than previous estimates indicated. By late August, Webb's infrared detectors resolved a carbon dioxide envelope spanning 348,000 kilometers, approaching lunar orbital distance from Earth. Yet spectroscopy revealed peculiarities. Iron-to-nickel proportions didn't match textbook cometary profiles. The molecular fingerprint looked skewed, like a passport with correct authentication stamps arranged in the wrong sequence. Compare this visitor to its interstellar predecessors. Oumuamua displayed no sublimation signatures, an inert body tumbling through the inner system without gas release. 2I Borisov conformed to standard cometary physics, predictable outgassing, gradual thermal fragmentation matching models. 3I Atlas occupies impossible middle ground, undeniably cometary in composition, yet displaying accelerations, mass loss dynamics, and jet organization unlike anything cataloged across natural comet populations. Here's what happens across the next 40 days. 3I Atlas reaches closest Earth approach December 19, 2025. Hubble and Webb are conducting intensive spectroscopic campaigns through late November and December. These observations represent humanity's only opportunity for high-resolution study. Once it crosses beyond effective detection range, the window closes permanently. The data gathered during these 6 weeks becomes the eternal observational record. No future study possible, no second chances. January 2026 marks the detection threshold fade. Spring passage carries it beyond Jupiter's orbit into the outer system, accelerating toward the galactic void. Every spectrum captured, every trajectory measurement recorded, every image resolved now will define what humanity knows about 3I Atlas forever. Pay attention to the timeline. Miss this observational window, and we'll never determine whether we witnessed remarkable natural fragmentation or encountered something the interstellar medium may contain that current physics doesn't anticipate. An object born in another stellar system drifted through cosmic darkness for potentially billions of years, then entered our solar system precisely when Earth hosts technology capable of studying it. The statistical convergence alone is breathtaking. Now, as it passes through our cosmic neighborhood, it's either demonstrating a remarkable natural phenomenon science must expand to accommodate, or revealing that interstellar space contains objects we never anticipated. Either conclusion is profound, but the window is collapsing. Observations conducted these final weeks will determine whether the millions of fragments are natural cometary debris dispersing according to orbital mechanics, or components of something far stranger. The disintegration is real, photographed, measured, quantified. The jets are real, documented across multiple independent observatories. The acceleration defied pure gravitational models, trajectory deviations calculated with precision. What physical processes created these phenomena will define not just what 3I Atlas is, but what stories the darkness between stars has been carrying. The telescopes are locked on, the data streams are accumulating, and somewhere in the spectroscopy, in the trajectory calculations, in the thermal models, lies the answer to whether millions of ice and rock fragments are following predictable physics, or whether something unprecedented just passed through our solar system during humanity's first moment capable of recognizing it.